In the past couple of videos on infinite series, we covered a bunch of different tests and also one really fun infinite series problem. Now, if you remember my first video on convergence and divergence, I titled it The Most Important Question, Part 1, and it covered what convergence and divergence is along with a few tests. This is Part 2, where it continues, and I'm going to reconcile all of those tests together in order to give a better example and view on how this stuff would work. So this will essentially be just like a bunch of videos stitched together, and how now there will be more stuff that you can learn from this video, and so you don't have to go reference every single one of those videos. You can look at one video. Also, in the future, I will be making a video covering everything on infinite series, which is pretty much like a full masterclass, so stay tuned for that. Without further ado, let's move on to our first test. What is the comparison test? Well, the comparison test is a test for figuring out whether a series converges or diverges. Now, if you don't know what any of these terms mean, then be sure to watch my last couple of videos, especially the one which is titled The Most Important Question, Part 1, as that covers the most important parts of what you need to know for this video. Now, how does a comparison test work? Well, the comparison test works by essentially comparing two different series. One series, we know whether it converges or diverges, and using that information, we can tell if the other series converges or diverges. Now, without further ado, let me introduce what I've created using Manim and how I can explain this to you. Let the infinite series of an and series adding up all the terms of a function b of n with 0 is less than or equal to a of n is less than or equal to b of n for all terms n. Now, number 1, if b of n converges, then a of n converges. And if a and n diverges, then b and n diverges. Now, this doesn't mean that if a and n converges, then b and n converges. That is not necessary. The converse of these statements are not true, as they normally say in proof logic. Now, let's move on to an example. We have two series. One will be our reference series, from n is equal to 0 to infinity of 1 divided by 2 to the n. This will be our reference series. Our next series will be from n is equal to 0 to infinity of 1 over 2 to the n plus 1. This will be the series that we're trying to test whether it converges or not. Now, if you look at all of the terms in this series, you will realize that 1 by 2 to the n will have the terms 1, 1 by 2, and so on. And the 2 to the n plus 1 will have 1 by 2, and so on and so on. And how does this work? Well, 1 is greater than 1 by 2, 1 by 2 is greater than 1 by 3, 1 by 4 is greater than 1 by 5, and so on and so on. And by our first rule that we said earlier about the comparison test and how it works, that means 1 over 2 to the n plus 1 converges. Our next series involves two series. Number 1, the one that goes from n is equal to 1 to infinity of 1 by n. This is the harmonic series, and it diverges. The next is n is equal to 2 to infinity of 1 over n minus 1. And this will be our test series. Now, if you look at all the terms, you see that 1 is greater than 1 by 2, and 1 by 2 is greater than 1 by 3, 1 by 3 is greater than 4, and so on. And sorry, over here it should be n is equal to 3 to infinity, not 2 to infinity. Sorry. Now, this is very good because all of the terms match precisely to the formula that we said earlier. But what if it doesn't? what if for some terms in the series it's greater than versus just being just always being less than or greater than or whatever it is. But for some terms, what if it doesn't follow the pattern? That's the main question we're trying to answer. Over here, we have two series. Number one, the series from n is equal to 1 to infinity of n plus 3 over n cubed. Now, this is our test series. The second series is our reference series of n is equal to 1 to infinity of 2 over n squared. Now, if you notice, over here, for some of the n's, you have that the first series is greater than the second series. But as you notice, it's only for a finite amount of terms. So that sum will be some quantity, we can call it m or x, whatever, some small quantity greater than the actual series. But from n is equal to 2 onwards, as you can see, all of it works perfectly. From n is equal to 3 onwards, all of it goes directly into the series, and the rest of it works. And what we know is that it's very, very simple that this series converges due to the p-series rule. And since the test series is less than that for pretty much every single term, besides the first couple, that means it's going to converge to some finite value, which will be slightly greater than the reference term, but that's not very important. All we mostly care about is, does the series converge or diverge? So, what did we learn? Well, we learned that for the comparison test, for two series, a to the n and b to the n, one of them will converge, not always, but b to the n. This shows that if there is a concept of a series being less than or greater than another series. Now, it might have felt obvious because some series converge and diverge, but this really solidifies it, literally using the fact that a series is less than another to prove something immensely fundamental about the series. The next is, what even is the comparison test? We learned the comparison test. And the final major thing we learned is that it doesn't have to work for every term, because that's why so many things have limits as n approaches infinity, because as long as there is pretty much an infinite number of terms, as long as a finite amount of terms don't work, it's fine, because infinitely more terms do work, essentially canceling out any possible effect that happens on the rest of the series. So, let's explain the test. Basically, let's say we have a series n is equal to 0 or 1 to infinity of a to the n. Now, basically, not a to the n, just like a of n. Now, what one can do is essentially, we can simplify a to the n. So we simplify to some form that is similar to something we already know. Then, what we do is we have another series. We say, alright, let's have this new series, b to the n, and let's take the limit as n approaches infinity of a to the n over b to the n. Now, if 0 is less than n is less than infinity, then it converges. If it is equal to 0, then if b of n converges, a of n converges, and if it's equal to infinity, if b of n diverges, a of n diverges. Now, essentially, what you'll notice is these two cases, it's just the comparison test. And that's actually very, very unique, since the limit comparison test has both this one extra case and the comparison test, the regular comparison test. So, one conclusion that we can draw from this is that LCT, or the limit comparison test, is a general form of the comparison test, or of CT. Now, since this one is a little more difficult to visualize and understand, I am going to walk you through a very quick example explaining how it works. So, let's have this series over here. N is equal to 1 to infinity of 3n to the 4th minus 5 over n squared. Sorry, no, not this. 3n squared minus 5 minus n to the 4th plus 2. Now, when simplifying these types of rational functions, let's look at the dominant terms, or the highest degree terms of these polynomials. So we'll get 3n squared over n to the 4th, or 3 over n squared. Now, as you see, this is very similar to 1 by n squared. So we can have that as our b to the n term. So all we do is simply we take the limit, and these two cancel out, so we just get 3. And since 3 is between 0 and infinity, it converges. And that's basically all there is to it. Now, the most guessworky-esque part is doing the new series, but all you have to do is just look at the different terms in the numerator and denominator. And the reason we can say, oh, just 3n squared over n to the 4th, is because as n approaches infinity, these constant terms become very, very useless and pretty much don't affect the series at all whatsoever. So, that's basically all there is for the limit comparison test. It's called the root test. So, let's explain it. Alright, so how does this work? Let's say we have an infinite series of some function f of n. Now, the idea is we take the limit as n approaches infinity of the nth root of f to the n. This is also the same thing as limit as n approaches infinity of f of n to the power of 1 by n. And there are again 3 conditions. The first condition is that if this is greater than 1. If greater than 1, then the series diverges. If it is equal to 1, the series is inconclusive. And finally, if it is less than 1, the series converges. Now, this is actually a very good way to see if another type of series converges. If you have any guesses, feel free to leave them in the comments and explain why. So, this series is the geometric series. Now, if you noticed, the geometric series takes the form of something or of some number to the n. So, n to the m. And if n is less than 1, it converges. And also, if it's equal to 1, series is inconclusive, but most of the time it will diverge. I'm pretty sure there are some exceptions, but feel free to say in the comments that if I'm wrong. Now, and let me show you why the geometric series converges. Now, what we have is, since we have this over here, we can do the root test on it. So, limit as n approaches infinity of m to the n, and then taking root m, or raising it to the power of 1 by n, gives us limit as n approaches infinity of m, which is just m. And if m is less than 1, then it converges, because the root test also says that it converges. So that's actually a proof for showing how the rules of the geometric series are there, as it's simply just an offshoot of the root test. Now it's not just that you're going to be using it for geometric series. the biggest case that you're going to use this is, let's say n is equal to 1 to infinity, is you have some function of n taken to the power of some constant, k most of the time, times n. And this is essentially the form where you want to use the root test. Now what it might also seem a little complicated as first, as the functions you might be dealing with something like 2n squared plus 3n to the fifth plus 7n cubed divided by 4n to the fifth plus 15n cubed plus 17n per se, or maybe instead of n cubed over here we'll just have 7. So this over here, and all of this is to the power of n, this in fact becomes very simple, since by the root test our limit as n approaches infinity will just be of this function. And you see the power is the same, so by the limit rules you have 3 over 4. Basically it's equal to 3 over 4, and it's less than 1, so we know it converges. If we try to do this by any other test, like the comparison test or the ratio test, it would be very, very difficult to evaluate it. So that's about it for the root test. We will be talking about another very important test, which is the alternating series test. Now, the biggest reason why this is so incredibly important is because it deals with such a wide class of series that it becomes very essential to solve most series, as not every series you're going to have all positive terms, and this is very also useful for stuff like harmonic analysis, etc., etc. So today we will be talking about that, and without further ado, let's move on to the video. Also, my fault if there's any background noise or anything. I try to minimize as much as I can, but sometimes I can't. So, what is an alternating series? Well, we talked about this in a previous video, but to recap, an alternating series is of the form this. Essentially, -1 to the power of n times b of n. Because as n goes from 0 to infinity, n goes through 1, which makes it negative, then 2, which makes it positive, then 3, which makes it negative, and so on, and so on, and so on, until infinity. But what's more important right now is that basically what it can do right now is series that would not normally converge. When you add this term, it does converge, because this -1, this negative and positive adding up, creates some very, very crucial cancellation. So, how would we know if they converge? Well, there are 3 main things. Number 1, that this term, b of n, is greater than 0. Now, that's just very simple. Most series will have that, and the reason is if it's less than 0, then you'll most likely have to adjust the series, although this is very trivial. The second one is much more important though. It's that b of n has to be greater than b of n plus 1. Basically, that means every term has to be greater than all the ones after it, or every term has to be less than all the terms before it. And number 3, what we have is the limit as n approaches infinity of b of n is equal to 0. That means this term over here has to approach 0 as n approaches to infinity. Now, if you remember, we talked about the harmonic series in a previous video and how this diverges. But if you have the same thing, but instead you have an alternating harmonic series, this actually converges, because this b to the n part, which is 1 by n is greater than 0. The next, every term is less than the last, so 1 by 2 is less than 1 by 3. Not less, what am I saying? greater than 1 by 3 is greater than 1 by 4, and so on. And 1 by infinity, which is the limit, is 0. So, in fact, all of these conditions are met, so the alternating harmonic series converges, but the regular one doesn't. Also, this video, I'm going to introduce you to something else, and that is called the different types of converges. Now, basically, there's another test, but it's basically within the alternating series test, and it's not really that like crazy. It's pretty much introduced with the alternating series test, so I thought there's no point of making another video. So here we go. What it is essentially is you have, let's say we have an alternating series equal to 0 to infinity, -1 to the n plus 1, b of n. Now, essentially, what happens is this series over here, this series, if it satisfies all three of these, is a convergent series, okay? It converges. But, let's say we have the term let's say if n is equal to 0 to infinity of just b to the n converges, then it is called absolute convergence. Basically, absolute convergence. Since if this is convergent, b of n, then of course -1 to the n plus 1 b of n, where it's alternating, so there's even more cancellation, will converge. But if it does not, like else, then it is conditionally convergent. And since it's not conditionally convergent, just means that the regular thing does not converge, but the actual series, the alternating series, does converge. One example of conditionally convergent series is the alternating harmonic series, because 1 by n doesn't converge, but the alternating one does. And one thing special is pretty much this stuff only applies to alternating series, thus another reason I chose to keep it in this video. So, that seems to me about it. Thank you so much for watching this video. See you in the next one, and bye-bye.